CoreWeave. For those of you who don't know us, CoreWeave is a specialized cloud provider. We basically build an infrastructure tailor-made for AI workloads. We compete against the big guys, Amazon, Microsoft, Google. Most folks find us to be a little bit better, a little bit faster, a little bit cheaper, and a friendly environment to build and serve models. Roughly 2 years ago, we met Stella and the Eleuther AI team. I'll admit we didn't quite know what we were getting into, like, kind of a group of hackers, interested in training a large open source language model. At the time, CoreWeave was very interested in helping to close the gap in kind of accessibility of large language models between what was available at the time, which I think was GPT3 was like the largest open source available model at the time, and then kind of the next step up was proprietary models built by huge AI labs like OpenAI.
And that one is relatively startup.
Yes, correct. So basically, what Stella and the team wanted to do was make AI more accessible. Philosophically, that aligned with CoreWeave. We were also really interested in helping to empower businesses to have access to better technology so they could build products, applications, user experiences on top of better models. Flash forward to January 2021. We had worked closely with the Eleuther AI team to build and support the infrastructure that they use to train and release GPT NeoX 20B, which was a huge step forward for open source AI. It sort of was a catalyst for a lot of other companies over the last 12 months to come out, release open source models, make this type of technology more accessible. Another great example of this was Stable Diffusion, released by Stability AI, who's we work with, who's closely related to Eleuther AI. And from an industry perspective, a couple of interesting things that I saw kind of from my seat at CoreWeave was a bit of a bottoms-up approach of AI last year, the types of companies that kind of were empowered to do really cool things, right? Companies who were really good at building products, applications, user experiences, maybe not necessarily data scientists or research experts to build some of these foundational models themselves, right? Maybe they didn't have access to capital to build the infrastructure. Maybe it just wasn't their cup of tea, right? So a lot of the work that Stella and the team did, in addition to empowering researchers, I'm sure you'll talk a lot more about the interesting stuff than I will, but from my seat, it was really cool to see all the work, innovation, and quite frankly, disruption that happened across the industry, largely in part to the work that Eleuther AI did last year and is going to continue to do for the foreseeable future here. So again, nobody wants to hear me talk. Stella's here, so I'm going to turn it over. But thanks everybody for coming, and without further ado.
We're grateful for it's been a huge help to us in getting access to resources, in teaching us how to use resources. It was a bit of a teaching each other kind of moment where we taught them how to work with researchers, and they taught us how to actually use large amounts of cloud computing resources. Today, I found out about 25 minutes ago, it's actually the 1-year anniversary of us releasing a 20 billion parameter language model to the public. I don't know if that was over your part, but I found that out earlier today.
No, that is happy coincidence.
I haven't actually spotted where the HDMI is, so I'm going to need a moment to attach my laptop. Hello? Can you all hear me good?
Yes.
Hello, my name is Stella Dieterman, and I am the head of Eleuther AI. Eleuther AI is a grassroots collective of researchers that focuses on open source AI, AI interpretability, and AI alignment. My background personally is in mathematics and theoretical computer science. I kind of got into AI by accident. I've been having a really good time working in it. So like I said, Eleuther AI is this grassroots collective of researchers. Like Max said, we've been working to develop open source AI models for about 2.5 years now. And when we got started by kind of some people dicking around in a Discord server. So Dodge is Connor Levy, the founder of Eluther AI, and he posted a link to the GPT3 paper a couple days after it came out. It was like, hey, we should try to replicate this. A little bit of the backstory is that Connor and some of the people in the Discord server had worked on replicating GPT3 back when that was the cool thing that had just come out. And so they got started. They started a Discord server. That's still where most of our research is organized. We put a high priority on both the public release of technology, but also on making the research process more transparent, more community-driven. Our Discord server is public. Anyone who wants to come and watch or participate in our research is welcome to do so. And we have research projects, with a lot of conversations about the state of the art of AI technologies. It's a great source for news, for information about what is new. And we have reading groups, we have speaker series. We had a Miri come last week, I believe. And we have people from around the AI community come and talk kind of about their research and about the things that they care about and stuff. So some of the work we're best known for, the Pile is a large data set, kind of a de facto standard for training large language models at this point. Releasing large language models, GPT-Neo, GPT-J, GPT-Neo-X. The language model evaluation harness is an open source framework we've developed in collaboration with Hugging Face and the big science research community for more reproducible evaluation of language models. We do some stuff in the text image space. VPN Clip is one of the early techniques for converting text into images. And clip-guided diffusion was an iteration on that. And we've also started working with people who are interested in the BioML space. So OpenFold is a large collaboration led by biology researchers at Harvard and Columbia that we were personally involved with and kind of helped them scale up their work in replicating AlphaFold 2, which is a state-of-the-art protein folding modeling algorithm. So Eluther AI is first and foremost a research community, and it's an open research community. It's very collaboration heavy. It's open to the public, like I said, and very frequently researchers at other institutions come in and hang out with us. It's kind of a very strange experience to be talking about this paper that just came out and have someone pipe up with like a very anonymous Discord handle and be like, oh, hi, I wrote that paper. So an example from last week, Alex Radford of OpenAI, I believe the lead author of GPT2, one of the prominent, one of the senior authors of GPT3, a major figure in the AI field, kind of just like dropped by to explain that our understanding of the way that they were evaluating language models on a particular task was wrong. We were struggling with replicating the numbers from their papers. They kind of gave us this walkthrough and wrote code for us to use to improve our evaluation framework. And this kind of experience is really shockingly common. When we were writing a paper about the largest language model we created, a 20 billion parameter model, we were having a lot of trouble reducing numbers from a benchmark paper by some researchers at Berkeley. And one day someone dropped by and was like, hi, so like I wrote that paper. One of my students told me that you guys were talking about this. Here's the thing that you're missing. And it kind of helped us do it. And it's been a really interesting and really great experience to be able to have this kind of feedback and this kind of input, even from people who don't participate in our community, who don't really, are not frequent posters or stuff, will come and provide information. And it's a really great to be able to get that kind of wide-ranging feedback. We have a lot of CUDA engineers from PyTorch, the PyTorch team, who are in our server and who regularly comment and help people with kind of advanced CUDA concepts and stuff like this is I think, a really great part of what makes our community so special. So a natural question is, who is in Eluther AI? So we are actually now an official legal entity. We formed a nonprofit, we're a research nonprofit. We have 17 full-time research staff and another 10 part-time research staff. Most of those people are students who are working part-time for us as well. We also have volunteers, interns, and a bunch of collaborators who come and talk to us about our research. All told, we have about 40 people who are regular and active participants in our research projects, and 100, 120-ish other people who are regular community participants, engage in conversations, talk about cutting edge research, but don't so much participate in the research that we do. So the thing that we're most well known for is open access large language models. On May 28th, 2020, a whole bunch of people at OpenAI dropped this paper called Language Models Are Two-Shot Learners, describing the GPT-3 architecture and the GPT-3 models. And this really lit a fire for a lot of people in the NLP community who became very interested in training similar models and having access to similar models, especially because OpenAI said, we're going to tell you all about it, but we're not actually going to give you access to it at all. And for about a year after this paper came out, very, very few people had models. Nowadays, most people can get access to the models via paid API. But for a long time, that was not the case. And researchers who wanted to kind of understand the capabilities, the limitations, and the biases of these models had to go train their own. And we were interested in doing that. We thought we were kind of early adopters of this technology and thought very quickly that it was going to kind of be a big part of the future of AI, and we really wanted to be able to play with it, to take it apart, to understand how it works, why it works, and what it's doing. And so in order to do that, we had to start training our own models because nobody else was looking like they were going to release any to the public. So when we got started, the largest publicly available GPT-3 style model was GPT-2. It was 1.5 billion parameters. There weren't really any large data sets for training language models. And there was very little public information about how to do this kind of work. I've spent countless hours scouring every inch of the GPT-3 paper. I was on a video call with some people a couple days ago, and I quoted a footnote in the GPT-3 paper by the page the footnote was on, which tells you a bit about how many times I've read that paper. And we kind of set out to say, okay, let's see what we can figure out. Let's figure out as much as we can, see how large models we can train, and kind of see what happens from that. And this was widely believed to be completely financially infeasible. Commonly floated numbers for the cost of training GPT-3 were between $3 and $10 million. And people straight up told us we were crazy. So GPT-3 was announced May 2020. Luther AI was founded in July of 2020. And by the end of that year, actually on December 31st, 2020, we released the pilot. So the first thing you have to do when you want to go train a large language model is collect data. And you could get data, and by data I really just mean like terabytes of text. Common Crawl is a Internet Archive-based project that kind of scrapes all the websites in the world and dumps all the data into a very, very, very large file that you can download. But that tends to be very low quality. It's not filtered. It's not cleaned up. There's a lot of code in it, and I don't mean like stuff from GitHub. I mean like HTML headers and stuff like that. There's a lot of junk in it. There's a lot of malformed text in it. So we put together like an organized effort to start generating collating, I should say, a large collection of curated text, because we thought that the guiding principle for developing a large data set should be, what do I want the model to learn? So we went and we took arXiv, and we took a philosophy repository, and we took the United States NIH medical papers repository, and we took Wikipedia, and we took Stack Overflow, and we kind of downloaded all of these things. And we just piled this data together, and eventually we had about 850 gigabits of text, which came out to 300 billion tokens after it's been tokenized for the model, and that is the number of tokens that GPT-3 is. So we did that, and we posted it on the line, and we said we're gonna train language models on this. So a couple of months later, we released GTP Neo, several models, but the largest, the 2.7 billion parameter model, was at the time the largest publicly available GPT-3 style language model in the world. Small caveat on that: throughout this entire time period, there's a 11 billion parameter model that was trained and released by Google around the same time GPT-3 came out, but it's kind of a different model architecture and does somewhat different things. And anyway, so a couple months later, we released a 6 billion parameter language model. And for a sense of scale, the large GPT-3 model was 175 billion parameters. So we have a pretty long ways to go from 6 to get there. And then about a year later, actually exactly 1 year ago today, we released the 20 billion parameter language model, which was at the time the largest publicly available language model of any type in the world. And something that I'm still immensely proud of and took a fuck ton of work. So here's kind of an overview kind of timeline of open models as well as closed models. On the left you have open models, on the right you have closed models. Open models are split between ones that you can download, but maybe have restrictions. So for example, OPT is models from Meta that has use-based restrictions. And on the right you have a variety of non-open source models that have various use restrictions. Some of them are cloud APIs, some of them have other release policies. And yeah, it's been pretty lonely for a while. For about a year and a half, we were kind of the only people training and open sourcing language models. And then in December of 2021, actually, while we were in the middle of training our 20 billion parameter language model, someone was like, hey, did you guys see the paper that Meta put out where they released a very large language model, like the largest one in the world? And we were like, fuck, how big is it? Turned out to be slightly smaller than the one we were training. But yeah, so they released the model, and Meta has kind of been the biggest actor in terms, other than us, in terms of releasing open source language models at this point. They've released a whole variety of models. The OPT models in particular are on par with, or the same size as GPT-3. They spent about a year training them and getting approval to release them. And kind of the really big thing that's changed, that's different today from a couple of years ago, is that even if the open source language models are still smaller than the state of the art, or still sometimes less powerful than the state of the art, they are in the ballpark, and they are things that researchers can actually use to do meaningful research on language models. And that's I think something that's really key. If back in early 2021, where you had access to GPT-2 and you were trying to understand the properties of GPT-3, you weren't going to get very far. But nowadays, even if the biggest, fanciest models are still closed source, I think that there has been a really big shift in what is plausible for researchers because of the fact that the state of the art for open source models has advanced so far. It is ultimately pretty close to what it is in general. So obviously we train in oops. Obviously we train and we release language models, but the reason we do this is because we want to study them. And one of the biggest areas that we focus on is what's called AI interpretability. And AI interpretability is a bit of a weird statement because what is there to interpret about these kinds of AI technologies? And I was thinking about how to explain this, and I think kind of the best analogy is actually animal intelligence tests. Biologists and psychologists spend a huge amount of time taking rats and putting them in mazes and designing these kinds of contraptions that your dog has to use to figure out how to get the food out of. And basically the way that these things work is you put an animal in a situation with some devices, and if they do the right things, they get food. And you do this over and over again, and eventually they learn how to solve the puzzle, how to navigate the maze, how to open the box, whatever it is. Language models kind of work the same way. When I say that I trained a language model, what I really mean is I built a box, and I put a language model inside of it, and I specified a way for it to get positive feedback, and then I left. And I came back 3 months later, and it was able to generate human plausible text and answer questions and do all of these tasks. But understanding how to go from the actual box I built to understanding the algorithms inside of the language model that actually allow it to perform the tasks that it performs is surprisingly difficult. So that is kind of in a nutshell what AI interpretability is about, especially with language models. And there are two kind of major projects about this that Luther AI does. One of them is what we call interpretability across time. So most interpretability research takes pre-trained models as kind of things given to you by God. Here's a model, go find out what its properties are, reverse engineer, and how it solves this problem. But if you really want to understand how to build better language models, that's not quite the best thing to care about in many cases. The thing that you really want to care about is how language models change as they are trained. How things that you do to them over the course of training actually causally influences their behavior, and especially what you can do as someone training language models to make better ones, to make ones that have desirable properties, to discourage the development of undesirable properties. And so this is a really big area of research for us, and this is something that this is what most of my research is spent on nowadays, trying to figure out how these models evolve over the course of training. And so I have a couple of applications of this I want to go through quickly. So social biases. This is a plot of roughly the y-axis shows how well the model understands social stereotypes. And so one thing we were curious about was, okay, can you take a model that is moderately biased and train it for a little bit to unbias it? So what we did was we took this model and this model that we had trained, and we rewound it about 1/7 of the way through training, 15%. And the thing we're measuring here is gender bias, the assumption that people of certain professions are men. And we replaced all masculine pronouns in the entire training corpus with feminine pronouns. We retrained the model for the last 1/7 of the data set. And we found that bias kind of stagnated, but didn't actually go down. And from that, what we've kind of learned is that social biases are learned early. You see a very large, you can't see my cursor, can you? No, you can't. You see a very large divergence early in training in the first 30%-ish, and then it kind of stagnates. It doesn't actually get worse for the rest of for the next 60%. So social biases are actually learned by these models pretty early on in training, and are difficult to unlearn. Obviously, turning all pronouns to feminine pronouns doesn't unlearn gender bias, but it is kind of the strongest opposite signal that you can give it. And we really found that didn't do a whole lot, which I thought was really interesting. Another thing that we found very interesting that a bunch of different researchers that have been looking at recently is how the actual frequency of facts in a data set influences the odds that a model is able to answer a question correctly. So kind of in some kind of idealized world, a model is able to answer kind of all reasonably short arithmetic problems with the same accuracy, because it understands something about arithmetic and it uses that to solve the problem. Turns out there's actually a very strong correlation between how many times a specific addition statement shows up in the training corpus and how likely the model is to get the question right. And so we were curious about how it kind of emerges over the course of training. And this is not a very easy plot to read, is it? So each of these boxes shows models of increasing size. So this is 160 million up through 12 million on the other side. And each of the different colors shows a different percentage of the way through training. So blue is the least trained, and brown is the most trained. And what these curves show is the correlation between training frequency and model performance. So the kind of interesting things that we see here is, first of all, there isn't really a whole lot of correlation for small models, because small models suck at arithmetic. Small models can't even answer what is 2 plus 2. Even if you train on them a lot, 10 to the 8 occurrences of the statement 2 plus 2 equals 4, the model still can't answer that correctly. But what we see for the larger models is actually that it's not that you develop kind of these capabilities as you just see text. For early in training, the blue line, the model's already seen most arithmetic statements at least once. At least most of the ones it's going to see at least once. And it's still pretty bad at all of them, regardless of how many times the data showed up in training. I didn't say this actually. The x-axis here is how often the data shows up in training, the y-axis is performance. But then it's biased towards, its preferential performance on high frequency stuff actually emerges over the course of training. It shows up very late. And so, early on in training it's not there, and then later on in training it starts to emerge, and then as the model actually gets really good at arithmetic, you can see the brown curves and the purple curves are more or less flat because the model's already getting 90+% of the problem correct. Another interesting area of research is understanding memorization. People care a lot about language models memorizing data for a lot of reasons. Some of it comes down to the law. Not to put too fine a point on it, most people train language models on data that they probably don't have the legal right to do that with. Another reason you might care about this is that memorizing someone's social security number or credit card number is bad. Ideally that number would not be in a training data set, but there's a lot of personal identity information that's just on the internet. And it's one thing if it's on the internet, but if it's on the internet and then memorized by a language model, that language model is able to reproduce it for a large for a large audience, that can increase the effective threat. So one question we asked was, is all data equally likely to be memorized? If you encounter data early in training or late in training, does that influence how likely you are to be memorized? We actually developed this theoretical model of how we thought memorization happened, and what this plot shows is quantiles, the y-axis is the theory of our model, the x-axis is the actual model, and the closer to the red diagonal line, the better fit the theoretical model has. And so our model actually fits it really well. What we realized after doing some kind of rigorous analysis and then experimentally validated was that all data is kind of equally likely to be memorized. Memorization is kind of randomly distributed throughout the training data set. This was ultimately kind of disappointing because going into this project, my mental model was that language models kind of intake data and process it and build this kind of representation of the world. And then they take more data and process the whole thing and build this like iterative representation of the world. And you would think that under that model, data you encounter early in training would be memorized less because it's been processed more times. The model has had more opportunities to build kind of naturalistic bases for it that are represented in ways that require it to not be totally memorized. And we found that that's just not true. And that has some really interesting replications for understanding kind of how language models learn, as well as on a practical level, like if my original hypothesis was that training order mattered a lot, that data encountered like say in the first 10% of training was basically never going to get memorized, that gives you kind of concrete advice as when training a language model. It says if you have data that you're worried is going to get memorized, put it in the first 10%, and then it's less of a problem. Because there's this really funny thing where, like I was saying earlier, most data we don't actually care if it's memorized. No one cares if your model memorizes like passages from academic papers or Wikipedia or arithmetic facts. What people care about is like PII and copyrighted text. And that ultimately tends to make up a pretty small fraction of your training data. So if there's something you can do, put it early in training, do something to it in pre-processing to discourage memorization, that would be really nice. Unfortunately, we haven't found a way to do that yet, but that's kind of something we're interested in. The other kind of interpretability research that we get into a lot at Luther AI is what we call interpretability across depth. So I'm actually going to jump ahead one slide. This is kind of a picture of a transformer. You start off with tokens, which are just like, think of them as letters, and then you embed them, you turn them into stuff that the machine understands, and then you have, this is a transformer layer. You have some attention heads, and then you have a multi-layer perceptron. And then you apply those attention layers to attention heads and the multi-layer perceptron several times, and then you run it through an embedding layer, and then you ultimately get probabilities over time. And the idea of interpretability across depth is that this is a explicitly iterative process. In contrast to like an RNN, there's a finite number of steps. Like GPT3 has 96 layers. There is, in some very real sense, 96 different things that GPT3 does in order to reach its output on an arbitrary input. Now, what each of those steps are is pretty complicated, but the fact that there are only 96 of them, and the fact that that number actually grows somewhat linearly with the size of the model, means that there's really good hope for understanding transformers as kind of these iterative phenomena where they actually take discrete steps and you can decompose and understand what happens at one step versus what happens at another step. And this kind of has a lot of potential as a way to understand how these models, what algorithms these models will implement, and how these models kind of come to their conclusions. We're interested in breaking them down, understanding them one by one. There's been really, really great research, especially from Anthropic AI and a company called Redwood, doing this with toy models. So one of my personal
one person whose papers I make sure to read every time they come out, his name is Neil Nanda, has this phenomenal paper where he trained a model to actually be perfect at arithmetic. And I don't mean perfect in distribution, I mean perfect out of distribution. This model could solve arithmetic problems several orders of magnitude larger than anything that you encounter at training time. It could do more complex arithmetic problems than anything you encounter at training time. It had arithmetic is a bit of an overstatement. It was specifically learning addition modulo a large prime. It really did learn perfectly how to add numbers modulo a large prime. And the only time it really broke down was when you tried to have it add numbers that were too big to actually get represented by the physical network itself. But the thing that's really amazing about this is he actually reverse engineered it. He dug into the weights and he dug into the performance of the model, and he figured out the actual algorithm that this model used to add things. And then he mathematically proved that does in fact implement an addition algorithm, and it is correct. But this was a toy model. It had one layer, and it was trained exclusively on arithmetic statements. And there's been other stuff like this since for these kind of toy models, but we're interested in larger models. We're interested in kind of understanding the actual algorithms being implemented by models like GPT3, and kind of reverse engineering those. So one kind of tool that we've been developing, this is actually currently under review. It's going to be released probably next month, or it's November already, so later this month, is this idea of stopping a computation halfway through. If these computations happen in discrete steps, you can say, okay, what has the model figured out after only 7 layers? And can you take what the model's figured out after 7 layers and kind of compare that to what figures out after 8, compare that to what figures out after 9, and look at the sequence and kind of use that to decompose what the model is thinking about. So in order to do this, first you need to be able to figure out what the answer to the question is. What does the model think the answer is after 7 layers? So we came up with this idea where basically after some point, we go through some of these attention layers, and then at some point we kind of just stop and we skip to the end, and we put an affine transformation. God damn it! I'm sorry, this part is slightly shorter than I want it to be. There we go. And so we can skip over the layers. And notably, doing this naively doesn't work. If you just cut the model after 7 layers and then kind of sew it together with the end of the model, the unembedding layer is what takes the implicit representations in the model and turns them into actual English. That doesn't work. And the reason for this that we figured out was that layers speak what you can think of as different languages. Kind of the representations that they use to represent similar concepts actually drift over the course of the model. Early layers and late layers have different representations, and so you need to add this additional affine transformation to convert from the language that model layer 7 speaks to the one that model layer 18 speaks, because the unembedding layer is skewed to model layer 18. So we need to translate from that into English. And what this allows us to do is kind of stop early in training and stop early in the computational process and understand what the model is thinking at different points in time. And this is super cool. So one thing that we've been doing with this is kind of looking at complex prompts for language models. So green is kind of solving a few-shot problem, and the x-axis here is the layer number. So early on, the model just doesn't know what's up. It gets the answer wrong. But eventually it figures it out and pretty much monotonically increases, or roughly monotonically increases. And then we tried something called prompt injection, which is that you can write prompts in a way that is reasonable to humans and misleading to AIs. It kind of convinces the model to do the problem wrong. And what we found was that those were only effective at the very end. Even when you prompted it with the prompt injection, oftentimes close to the end of the model was close to the end of the architecture, the model actually had a pretty good score. Not quite as good as with few-shot examples. I should have done this 0 shot because the red line is 0 shot, and that would have been more fair. And then at the very end, performance plummets. And what I think is really cool about this is it lets you look at kind of warring impulses within the model. One of the biggest things I've learned working with large language models is that Oftentimes the reason why they don't answer your question correctly is because they don't actually know what they're supposed to be doing. They've been trained on a wide variety of disorganized and poorly curated text, and it's very difficult to it's a real skill to convince a language model to know what task you're trying to do. This is actually the problem that ChatGPT solves. ChatGPT is not smarter than like GPT-3. If you're an expert at using GPT-3, you get the same quality of results using ChatGPT. The difference between the two is that ChatGPT has been adapted in a way that OpenAI has found is more accessible to its users, and decreases the amount of skill required to get good responses, and raises the floor for using it. And that's definitely useful information, though I kind of am forgetting why I thought that was relevant in the moment. But where are they going with this? Yes. Oh, warning impulses in the model, right. So one kind of inspired by this, one thing I'm very interested in is understanding how the model kind of decides what task it's supposed to be solving. So what you can see is that like by layer 20 of this model here, or 30 of this model over here, the red and the green lines are pretty close together, especially because the green line is few shot and the red line is 0 shot. The model has mostly figured out the task. And then later it changes its mind, and it thinks it's supposed to do something else. And it's wrong, and it ends up producing like basically an accuracy of 0. It gets the question completely wrong, but it changes its mind about what the problem it's supposed to be solving is. And as a result, the performance kind of plummets. And the idea that you can locate the task identification aspect of how these models work in particular layers, I think is a really, really fascinating. And I hope is going to lead to both developing better models and also developing better understandings of kind of how these things work and what processes they can implement. One potential application of this is that you can use early stopping to improve robustness. If the model's performance has been monotonically increasing, and then it kind of like plateaus or it goes down, like maybe you should just stop early. Like for specific questions, if the model wildly changes its mind about the output of the answer to a question in layer 30 or 32, maybe you should just ignore that and go with what earlier layers had thought. So yeah, those are kind of like some of the major research projects we have going on in Ulithir AI. We also do stuff in other modalities. Transformers have kind of started off in NLP, but have kind of expanded to the world at large at this point, honestly. Like, they're sort of everywhere. And so we've been working with transformers and also transformer-adjacent architectures in various other contexts. So text image synthesis is like one of the sexiest things in AI right now. This is something we've been working on for a very long time. That's a radiator. I do not miss that. Having central error is amazing. So we've developed some algorithms for doing text image synthesis. Here are some examples of that. We've worked on so these text image synthesis models, kind of at their core, a core component of how you train them is this idea of a contrasted model. You have a large pile of captioned images, and you separate them, and you provide the models the images and the captions separately, and you train the model to pair them up. And that's how it understands how to map text images. Typically, the model people just use is called CLIP. But you can use this kind of concept in other contexts. So we've been applying this to storytelling. A bunch of our researchers are very interested in computational tools. And so we've developed models that can actually like write reasonable critiques of stories. The idea is that instead of feeding it image and captioned image, you feed it text and criticism of that text. Or code and git diff is something that we're working on right now, where you train on the actual code and then like the edit a human made to that code to change it. And the idea is that you're hoping to learn kind of the steps that you're supposed to take to iteratively improve things. And the idea is to create kind of a better sort of writing assistant type thing. So we've worked on this in storytelling and also, like I said, in code. We've also worked on this in biology. Clip-like models are extraordinarily useful in all sorts of applications. We've been developing ones for understanding protein sequences, for understanding the relationship between English statements about biological facts and DNA, and we've been doing stuff like that. How much time do I have? I have no idea.
7:30.
What?
7:30.
7:30. Okay, I'm reasonably on time now. We've been working with a whole bunch of people to replicate AlphaFold 2. This was kind of something that started at a bunch of different institutions independently, and then we kind of all got together because why replicate each other's work when we can just join forces. So I mentioned this earlier, but this is led by people at Columbia and Harvard, and then another dozen and a half institutes ranging from universities, University of New York, Mount Sinai, some biotech companies like Genentech, scientific computing companies, NVIDIA, Luther AI, New Zealand Hamilton, Stability AI, all sorts of companies. And we kind of just re-implemented and redeveloped the AlphaFold 2 model, which for anyone unfamiliar is a really revolutionary algorithm for predicting how proteins fold. Loosely speaking, proteins in your DNA your DNA tells your body how to build proteins, and it tells them what sequence of chemicals to put next to each other. And they come out in a line. But then because of electromagnetic forces, they actually fold and form these complicated 3D shapes. And the geometric shape of a protein is actually extremely important for understanding how it behaves. And so being able to take a strand of DNA and predict and determine what protein it codes for is fine, but being able to predict how that's going to fold, what shape it's going to take is actually extremely important and a huge limitation to a lot of current problems in biology. There is now an algorithm that does that as well as any human. The kind of crazy anecdote about this is that there's a semi-annual protein folding competition for AIs. When AlphaFold 2 was entered, there was one problem out of the however many problems there were in the competition, and the AlphaFold 2 didn't have the best answer. And they were like, wow, this model's really, really good. It was the first time a model had gotten the best answer for almost every protein. And the judges went and looked at it, and they realized that the answer key was wrong. And then they fixed the answer key, and AlphaFold 2 is the best model at that protein as well. So you know you're good when they use your answers to double check the answer key. So this was developed by DeepMind, and we kind of replicated it. We publicly released it, and we publicly released its training code because DeepMind never really did that. So you can now train it further. You can train it on your own data. You can explore kind of how it behaves. We learned some really crazy cool stuff. Do I have that video? I do have that video. So the coolest thing that we learned about how this model behaves, this kind of goes back to my interpretability interest, is that over the course of training, what you see on the plots on the right-hand side here, the x-axis is the number of training steps, and the y-axis is something complicated that doesn't really matter. But over the course of training, the geometric understanding of the model changes in very well-defined and discrete categories. So the different colors actually represent different dimensions, as kind of the key kind of indicates, and it's probably easiest to show in the video. So what this shows you, so we have a single protein, and what you're about to see is the model's guess for how that protein is going to fold at various steps in training. So let me figure out this. There we go. So early on in training, this is a little under 2,000 steps in, you have this very flat structure. Oh, you have my person. You have this very flat structure. It's basically 2D. Or sorry, it's basically 2D. And then later on in training, it's now kind of spread out. And so it's no longer a line, it's now this, it fills up the plane. But as you can see as it rotates, it's pretty flat, all things considered. And then as training goes on more, it becomes this more full 3D structure. And then as training goes on further, it fills out the details. And this is a standard biology thing, but as these curves get thicker, that's a representation of the details getting filled out. So at this stage, you have this let's go see that happen again. Right, so this is a pretty 3D shape. You have wiggles in all three dimensions. But very early on in training, you don't have that. You have this basically line. And This is actually just and now it's a plane, and then it becomes a 3D. This is something that happens consistently across all proteins. And not only that, the representations very early on in training are actually roughly optimal if you assume that you're only allowed to work in a certain number of dimensions. So when it has this like flat representation of this protein, this is pretty much, oh, that was not quite correct. There. This is pretty much what this protein looks like. Oh, in terms of being instead of my apologies. There we go. Spacebar works. So this is pretty much what this protein looks like if you project it into 2 dimensions. And so it gets this like near optimal understanding of the arrangement of the protein, but only in 2 dimensions. And it takes further training for it to learn more dimensions, and actually adds more dimensions as it trains. And that's, I think, just a really, really fascinating thing. I've never seen a property like that happen so clearly in a model before in my life. But watching the geometric understanding and then kind of using these thickenings as filling out the details, and then the geometric understanding of these models evolve over the course of training is really just like incredible. This is, for the record, my vote for the coolest paper I've been affiliated with like in the past year. Didn't do a whole lot. I mostly helped people scale things to be bigger, but this paper is phenomenal. Please go read it. And that is, I think, what I have. Yeah, a couple of acknowledgements. I want to give a huge shout out to Connor Leahy's, Leo Gao, and Sid Black. Those are the 3 people who founded Eleuthera AI originally. So kind of what happened, I mentioned that we're now an official nonprofit research organization. What happened was we started off with being a bunch of people hanging on Discord server doing stuff in our free time. And stuff we were doing that was really cool, and so we started getting hired to go do that professionally. So Leo now works at OpenAI, Sid and Connor have their own AI company. And so what we saw was over and over again, kind of many of the leading figures in our organization just got hired to go do the thing professionally. And so it became pretty clear to us pretty quickly that if we wanted to keep our friends and kind of the best talent around, we need to be able to pay them, because at the end of the day, as much as you care about doing stuff in the open, like doing it for money is a lot better than doing it in your free time on the weekends. So yeah, I want to give a huge shout out to Shivanshu, Curtis, and Lewis, who with me lead Eleuthera AI nowadays. We have dozens of employees, volunteers, and collaborators who have made all of the research we've done, all of the models we've released possible. And then, a bit more on a personal level, Ellie Pavlik, Callum Raffel, and Raph are 3 people who have been phenomenal mentors to me. As well as to our wonderful sponsors, including CoreWeave, who sponsored this event. These companies, and mostly companies, have really donated a huge amount of money to our organization and enabled the very expensive, very complicated research that we do to be done in a really unprecedentedly open and uninfluenced by corporate interests at the end of the day fashion. Yeah, come join us. Send us an email, send me an email. We have a public Discord server and a website. I'm currently revamping our website, so maybe come check out our website in 2 weeks when I launch the new version, because the new version is a lot better. But come check out our Discord server and come learn about AI, because there's a lot of very cool stuff happening in the field of AI right now, and we love sharing information with you people. Thank you very much.
Maybe we can open for some questions.
Yeah, totally.
Yeah, if folks have any questions.
I have a couple.
Yeah.
So you alluded to it at the end, and obviously we heard about this in the opening remarks, but one of the...
Sorry, go on.
Yeah.
I was just confused by my computer.
That's fair. One of the early challenges you mentioned that a lot of naysayers were talking about was it being financially prohibitive. Do you mind sharing how much the cost ended up being for you guys over the last couple of years of training these models?
So first of all, no, I definitely don't mind. That question is a little complicated. So we haven't paid for most of the models that we train, because people give us competing resources for free. If you look at GTP New X 20B, there's an actual number to answer the question in that paper. in the associate program with someone that it's a couple $100,000 to train that model on commercial cloud services. Sorry?
So, the cost would be the training training?
96 A100s for 3 months.
It's like $750,000.
$750,000, yeah, that's over 3 months. So 96 A100 GPUs for 3 months. That we were allowed to monopolize them for 20 billion parameter model. 20 billion parameter link from about $300,000 to $400,000.
Honestly, that order of magnitude is a lot smaller than I thought.
It's really, really interesting. So the main thing that's driven down the costs of training these models is actually the advance of technology. The people you have to thank for that number being an order of magnitude smaller than what it would have been 3 years ago are NVIDIA.
Yeah.
Every generation of GPUs are far more efficient and, more importantly, far more cost efficient than anything that really come before them. So kind of like concretely, like GPT3 was trained on what was at the time the state-of-the-art A100 GPUs. The next generation are called A100s. A100 GPUs are, for these purposes, about twice as fast and about 30% more expensive. And the newest GPUs that are currently in the process of coming out, the H100s, are, I'm not sure if I'm allowed to say this actually, because I've early access to them.
Okay.
But they are also like a lot more cost effective, a lot cheaper per operation basically.
Yeah, you can assume
really
those are
driven
like
down.
4 times as performant on the training side, not nearly 4 times the cost.
Yeah.
Twice the cost.
Wow.
Like a factor of like a savings factor as you increase the generations of GPUs of between like 1.3 and 2 is like has been typical for the last 3 releases of NVIDIA GPUs, and it's insane.
That's wild.
And I actually kind of alluded to this earlier. Like people were estimating GPT3 would cost like $3 to $10 million. By this coming summer, that number is probably going to be like $500,000 because H100s are just that much better than E100s. And to a lesser extent, advances in computational or advances in how we design these models have been improved. Flash attention is a very recent development that is I'm gonna not get on my soapbox about this. There have been some algorithmic improvements as well that have helped, but by far and away, the biggest improvement has been just new generations of GPUs are just much better at doing this thing.
Wow. Thanks.
Did you have several questions? Do you have
I
another?
have another one, but if
Anyone else have a question?
I have a question.
Yeah.
I'd like to better understand data memorization. Sometimes ChatGPT can act kind of like a Wikipedia. If you ask the height of a celebrity, it'll give you an answer. So it feels like it's not machine learning. It's kind of like I know it's not doing some search, but it kind of like it's memorizing the entire web, and or if it's machine learning, it feels like it did some like crazy overfitting.
So this is actually one of my favorite phenomena because you said it's not really machine learning. Throughout history, this has been the case for like the past 50 plus years. Things are only counted as AI when they're hard. Once they're easy, they're no longer AI. If you go read like AI papers from the 80s, they're talking about like AI problems that you look at and you're like, that's even considered AI. I think in 5-10 years, people are not really even going to consider like bots that can play chess as artificial intelligence. Oh, they're just programs that like know how to play chess. It's a very large search tree, can search it faster than humans, so what? And this is kind of a experience that has happened for a very long time. Once upon a time, if you could have an algorithm that could tell the difference between computer font and handwriting, that was considered artificial intelligence. That sounds kind of weird today, and you kind of see this happen over time. So I just love commenting on that because I find that phenomenon very sociologically interesting. So ChatGPT is actually a strange example because it has different memorization properties than other types of language models. One of my collaborators, their name is Janice, has done some really interesting research on this where ChatGPT has like a very strong, is a lot more deterministic. if you think of the input to one of these models, like you could frame your question slightly differently a whole lot. Most models are pretty sensitive to different framings, and will sometimes change the content of their answer, and very frequently change the style of their answer based on your framing. ChatGPT is a lot more consistent. It's also a lot more consistent in a literal determinism sense. Like ChatGPT has a favorite number. If you ask it to name like a random number, it is like 1,000 times, it mostly names the same number. It's a very, very concentrated distribution, and it's not true for other types of language models. So something in the way that they kind of do their instruction tuning actually like instills in it like very consistent behavior, which I suppose is probably desirable in terms of instruction following, but does kind of have these like weird kind of caveats. Yeah, I mean, there's a sense in which there's good memorization and bad memorization. Like, if the model memorizes that 2 + 2 = 4 instead of really learn that 2 + 2 = 4, like, do you care? Not really. Like, it's still giving you the right answer. And then there's obviously bad memorization. I think at the end of the day, like, a lot of our human intuitions for what constitutes memorization are poorly captured by most ways that we have for understanding that concept. And so I'm not really answering your question. I mean, concretely, the answer to your question, ChatGPT is a GTP model that's been fine-tuned based on feedback from humans as to what responses they like and what responses they don't like. In response to questions about like things like people's biographies, people tend to like answers that look like Wikipedia. That is why ChatGPT answers questions like Wikipedia. It's been explicitly trained to do so. That's the short answer to your question. I hope the ramble was interesting, at least. Yeah?
Related to memorization, earlier you said that stereotype is learned early but difficult to break, but later on you said that there's no order in the memorization. Memorization happens.
Yes.
So what's the difference between the two?
We don't know. I am very interested in finding out. I'm going to be spending a lot of time trying to figure that out. What we see kind of consistently is that different types of behaviors emerge at different points in training. I almost put a plot about this in this presentation actually. But different types of tasks are learned at different percentages of the way through a typical training focus. So the ability to like identify that a sequence has been repeated a whole bunch. So like if you input to a language model the same letter over and over again, like 20 times, it will be pretty good at just repeating that same letter back to you. It understands that this is just a repeating sequence. That kind of copying data over, once it's identified as repeating, happens very, very early in training, like the 0.1% early in training. There's a really good plot about this in the Scaling Laws paper by OpenAI, the original one, which I didn't understand at first. I didn't realize the x-axis was logarithmic. I was like, but anyway, very early in training, stuff like data repeating is understood, and the model learns to kind of implement that. And then other more complicated behaviors occur later in training. My kind of personal theory is that, so language models don't just reproduce biases in data, they actually exacerbate them. This is true kind of consistently across modern AI. Most AIs are much more biased than the data that they were trained on. And kind of my personal pet theory for this is that these models are very good statistical models that have a good understanding of latent factors that have high explanatory effect. Racism is a latent factor that has high explanatory power. And so kind of my theory is that most kind of standard measures of social, of race, of gender, of religion, like whatever, socioeconomic bias, are basically pattern matching. The model understanding like this is a pattern that I typically see for men, so I'm going to repeat it I'm going to assume that in this context it's a man. This is a pattern I am typically seeing for people who have been identified as black, so it's going to reproduce it for black people. So that's kind of my theory, that this is learned very early because it's not really we think of racial bias as a very complicated phenomenon. But I mostly think it's about pattern matching more than about kind of actually understanding the complex social dynamics. There's been some preliminary research from the AI ethics and the sociology of AI communities about this, where the biases of AIs don't actually line up with human biases. Like at a high level, they're oftentimes the same. Like the model, like a chatbot is typically going to be better at stereotyping a black person as committing violence, or a white person being rich, or like whatever. But the details are often different. And especially when you start looking kind of at subclasses and looking at differences in stereotypes between like WASPy people versus white Jews in America. That's something that models have a lot more difficulty understanding. And in my mind, that kind of lends credence to this idea that it's basically doing gross pattern matching. It's just like a very large data set, and it has this high level of pattern matching that emerges very early. Yeah.
I have a question. If you were a tech investor interested in generative AI, what kind of companies will you be looking at investing in?
I don't think that's a question I can fairly answer.
Okay.
to be
That's fair.
totally honest. I mean, you should invest in us. You should give us money to do the research. We're awesome. I mean, I think most of these companies are pretty awesome. But like, like at the end of the day, like this is a question that I'm highly biased on. I know people at CoreWeave, I know people at Stability, I know people at Google. I have a very high thought of them. But that doesn't mean that people at other companies are not as good or equally valuable. It's just they're not the people who have been supporting me, who I've interacted with the most. So I don't think I can really answer that question fairly. Yeah.
You talked a little bit about researchers being able to reverse engineer the algorithms that LLMs use. What is the state of the art around LLMs and AI explainability?
So there's a couple different ones depending on what it actually is that you care about. In terms of reverse engineering, it's this paradigm called circuit interpretability. The basic idea is that if you this is like an OK diagram for time optimization. I actually stole this from the circuit interpretability paper. But yeah, so it's this paradigm developed mostly at Anthropic called circuit interpretability. And the idea is that the idea is that information flows through this network. It starts off as tokens, you embed it, and then, so this is like a residual class. So all of these things are x plus MLP of x plus attention of x. So here is in the middle of your representation of the residual stream, and then you kind of read information out of it, process that information, and then use the results to impact the residual stream again. And the way that these circuits work, or these circuit models work, is that they draw large circles around things, and they say, I don't understand what's happening inside of the circle, but I understand how information flows from one piece of the circle, from one circle to another. And I can kind of explain, if, hypothetically, this box that I've drawn performs this operation, then as the information flows through the network, you can see this kind of thing happen at its state. But basically, it's most of the really cutting edge for reverse engineering neural networks comes down to decreasing what is considered the black box. So like you can have your standard view, like the entire thing is largely a black box. But by looking at information flow, you can shrink those black boxes to individual things. Say, I don't understand how the model actually does this kind of operation, but I can see that it sees the number 7, it sees the number 5, it does something, and it spits out the number 12. So that something is probably adding, even if I don't understand why these parts of the network together can do addition. For very basic models, there are actually explicit reverse engineering. I have this open right now, actually. So, no, but I can close it real quick. So I guess okay, so I guess I can't pull it up. But there is a, here it is, we haven't talked about this earlier. If you train a small transformer to do arithmetic, or to add numbers modulo p for a large prime, it does it with, I'll let you go for it, there we go. It does it with this algorithm. And this has kind of been concretely figured out. Arithmetic is kind of a relatively easy example because when, like I said, when you see the 5 and the 7 go in, you see the 12 come out, it's not that hard to figure out it's doing addition. But for these like very small toy models on very simplified problems like adding numbers modulo p, we actually have explicit algorithms you can break down into steps, see how it does each of them. And people have kind of identified this. The big challenge with this is making this relevant to models that people really use. I've been talking mostly about models that have between 10 and 200 billion parameters. This model has like 200. So making this relevant to real world tests is actually really challenging. There is a really cool recent paper that has done that as well for this task called indirect object identification. So the idea is that when Mary and John went to the store, John gave a drink to blank. The task is to identify which person is supposed to go in that blank. And the answer is it's the person who hasn't been mentioned multiple times. And so this paper actually shows, has figured out what the model does. Is it basically makes a list of all the people, and then skips over the ones that appear twice. And it ends up with just John. No. With all people, John is the person who appears multiple times. So it returns. I did not make Mary. That was going to. Here's kind of a circuit diagram. So what this is a representation of is how is attention patterns mostly. And so these are things attention heads do that have been descriptively labeled based on humans looking at data going in, data coming out, and kind of reaching high-level conclusions of what behavior it's doing. So duplicate token heads detect when tokens show up multiple times. So this is the one that sees that John shows up multiple times in sense. Previous token heads just look at the previous token. Induction heads are a fancy term that Anthropic came up with that basically refers to any time that you're copying data. So this isn't like logical induction. This is more like iteration, I guess. It takes early data and it repeats it again. And so basically what this diagram says is that you have three types of heads. You have ones that keep track of what previous tokens you've seen at all. You have ones that keep track of which tokens you've seen multiple times. And it's not shown in this diagram, but there's another head that kind of subsets to things that are names. And then the induction head looks at the list of previous tokens, the list of previous tokens seen multiple times, and picks out the one that doesn't show up twice. The thing that's not on both lists. And yes, an emission head decreases the probability of the other names. Sorry about that. And so this has been done in GPT3 small, which is like a 125 million parameter model. One of my researchers has replicated this on slightly larger models, but doing this on several billion, 10, 100 billion scale parameter model is still very much not in the cards at the current moment. Kind of doing this kind of task-based decomposition. So the way that each of these heads are named is you literally look at a lot of data going in and a lot of data coming out, and you're trying to guess what the black box is doing. And then you can understand how those heads are wired together and how that corresponds to the task that you are interested in. Yeah.
30 seconds or less, because I know we're running short of time.
Sorry.
How do you see these models evolve over the next 5 to 10 years?
That's a great question.
I know it's difficult.
I mean, so the first answer I have to give is, who the fuck knows? The state of the art 4 years ago is unrecognizable today. Frankly, it is the field has changed so much in the past 5 years that the idea that one could forecast 10 years and 15, 20 years in advance is, in my mind, a little bit ludicrous. In the next 2 years, what's currently hot is incorporating data from multiple modalities. So text-to-image modeling obviously blew up last year. But doing that in a variety of domains and doing that beyond the kind of standard text-to-blank generative context is becoming really big. So doing question answering, so being given a picture and a text question that requires you to look at the picture to answer the question. And figuring out the answer to that question, kind of other ways of incorporating information from multiple modalities, as well as using modalities that aren't text or image. So there's been a lot of work on audio. There's either a model that's about to come out or a model that has just come out. I don't actually remember. That synthesizes, that does text that reads things aloud in a like human-like voice, extremely compellingly. Whisper from OpenAI can do it in reverse. It takes audio and transcribes it. And kind of my view of this is that language models at their core are very reasonable at reasoning. And on a training efficiency basis are kind of the best ways that you can currently teach AIs to do reasoning. So what I see happening is a lot of people building these components that translate from domain 1 to domain 2, and then using a language model kind of as the core reasoning device. We've seen this a little bit in text domains in the past, where there's a paper called like, you can give GPT3 a calculator, I think, where basically it realized that you can have like GPT3 like read a paragraph that has like a math word problem, but if you outsource the actual addition to an actual calculator, the performance goes way up because it's very good at understanding the task. The problem is it just gets the arithmetic wrong. And so this idea of using language models as reasoning agents and feeding data in from multiple modalities and then using like custom models, maybe literal calculators, maybe custom heuristics, maybe custom search algorithms to answer specific difficult problems that current language models struggle with is, I think, a really promising thing. There's been some research at Google and DeepMind both independently about doing this with robotics and training robots to like follow human descriptions of tasks. And kind of the idea is that it processes the text input, it models that it understands what it's supposed to do, and then it uses a not LLM-based search algorithm to actually go solve the maze or lift its arm or whatever, because that's not something that LLMs are any good at.
Yep, we're